we shall going to start module 3 of chapter 5. In this module, we shall discuss extended Hamilton's principle and its uses. So far, we have discussed the Hamilton's principle, which is basically a variational principle and differ from the differential principle a lot. Variational principle is very much helpful as it is invariant under a specific choice of coordinate system. Hamilton's principle is applicable for a conservative dynamical system. We shall extend this principle to include non-conservative system and will establish Lagrange's equation of motion in a non-conservative dynamical system. In this module, we shall discuss Hamilton's principle, which will be extended to include non-conservative dynamical system, and we shall deduce Lagrange's equations of motion in a non-conservative dynamical system using the extended Hamilton's principle. Now, extended Hamilton's principle. We can generalize the Hamilton's principle known as extended Hamilton's principle to include non-conservative forces, so that Lagrange's equations of motion for non-conservative system can be derived. The motion of the system between the times t0 and t1 is such that the line integration t0 to t1 capital T plus W dt is stationary for actual path compared to the neighboring paths between the same two terminal points. That is, if we take the delta variation of that quantity, we get delta integration over t0 to t1 capital T plus W dt equal to 0 for motion along the actual path. Here capital T is the kinetic energy and W is the work done by the forces acting on this system. Proof. Consider a holonomic dynamical system. Let delta r vector denote the small virtual displacement of a typical particle of mass m of the system whose position vector is r vector at the instant t. By virtual displacement, we mean that the position of the particle changes but time remains fixed. From D'Alembert's principle, we have summation over I mi ri vector double dot delta ri vector is equal to summation over I fi vector dot delta ri vector. This gives the virtual work done by the forces acting on the dynamical system, which is given by delta W. Here ri vector double dot is the acceleration vector. So, mi into ri vector double dot gives the force vector. Now, delta ri vector is the virtual displacement vector. We are considering the dot product, that is scalar product of two vector quantities, which gives the work done. On the right hand side, Fi vector is the externally applied force. we are taking the dot product with the virtual displacement vector delta ri vector and fi vector, which gives the virtual displacement. From D'Alembert's principle, we have obtained this result. Now, summation over I mi ri vector double dot dot delta ri vector can be written as ddt of summation over I mi ri vector dot dot delta ri vector. If we get the derivative, we can get two terms here, but in the previous equation on the left hand side we have only one, so we have to subtract one term which has been written in the left hand side as second term. Now, let us calculate the time derivative. First of all, we are considering delta ri vector as fixed and taking the time derivative of mi ri vector dot, we get mi ri vector double dot dot delta ri vector, which is the left hand side of the previous equation. Now, keeping mi ri vector dot fixed, if we consider the time derivative of delta ri vector, we get the extra term which is mi ri vector dot dot ddt of delta ri vector, which have been subtracted here. Right hand side is written as it is. In the next line, first term has been written as it is. In the second term, we have interchanged the delta operation and ddt operation and get the second term of the third line. Now, ddt of ri vector can be written as ri vector dot. Using this, we get equation 5.2. Thus, we get ddt of summation over I mi ri vector dot dot delta ri vector minus summation over I mi ri vector dot dot delta ri vector dot equal to delta w. Here ri vector dot means ddt of ri vector and ri vector dot dot delta ri vector means we are considering the scalar product of two vector quantities, which is velocity ri vector dot and virtual displacement vector delta ri vector. Now, the kinetic energy of the system is defined as capital T equal to half m v square. Here v is nothing but r vector dot. So, capital T is equal to half into summation over I mi ri vector dot square. If we consider the virtual change of kinetic energy T, then we get delta T equal to summation over I mi ri vector dot dot delta ri vector dot. Substituting 5.3 in 5.2, we have ddt of summation over I mi ri vector dot dot delta ri vector minus delta capital T equal to delta w. Since ddt of summation over I mi ri vector dot dot delta ri vector equal to delta capital T plus delta w equal to delta capital T plus w, we have integration over T0 to T1 delta capital T plus W dt equal to summation over I mi ri vector dot delta ri vector taken at t0 and t1 gives the result 0. As the end configurations are prescribed, so delta Ri at T0 vanishes and delta Ri vector at T1 vanishes. Now, we shall deduce Lagrange's equations of motion for non-conservative dynamical system. So far, we have deduced Lagrange's equations of motion for a conservative dynamical system. Here we consider a non-conservative holonomic dynamical system having capital N particles specified by small n generalized coordinates given by small q1, q2 up to qn. Now, the extended Hamilton's principle, which are applicable for non-conservative holonomic dynamical system, gives delta integration over T0 to T1 capital T plus W dt equal to 0, or integration T0 to T1 delta capital T dt plus integration T0 to T1 dw dt equal to 0. Let capital Fi vector be the force acting on the particle and Ri vector is the position vector of the same particle. Therefore, position vector Ri vector can be considered as the function of generalized coordinates q1, q2 up to qn and time t. So, Ri vector equal to Ri vector function of q1, q2 up to qn and t, I varying from 1, 2 up to capital N. Let capital Qj be the generalized forces associated with the generalized coordinates small qj for j equal to 1, 2 up to n. Then delta W equal to virtual work done due to virtual displacements delta Ri vector at time t, which is given by summation I equal to 1 to capital N Fi vector dot delta Ri vector equal to summation over I equal to 1 to capital N Fi vector dot summation over j equal to 1 to small n del Ri vector del Qj delta Qj equal to summation over j equal to 1 to n summation over I equal to 1 to capital N capital Fi vector dot del Ri vector del Qj delta Qj. Here we have interchanged the summation. This gives summation over I equal to 1 to capital N capital Fi vector dot delta Ri vector equal to summation over j equal to 1 to n capital Qj delta Qj, where capital Qj equal to summation over I equal to 1 to capital N capital Fi vector dot del Ri vector del Qj. In our previous module, that is module 2 of chapter 5, we have established Hamilton's principle, which is valid for a conservative dynamical system, and using that principle we have deduced Lagrange's equation of motion, which are applicable to a conservative dynamical system. But there are non-conservative dynamical system also, so we have to need the Lagrange's equations of motion in non-conservative dynamical system. We have extended Hamilton's principle to include non-conservative forces, and using this extended principle we shall deduce Lagrange's equations of motion valid in a non-conservative dynamical system. If we substitute 5.17 in 5.16, we have integration T0 to T1 delta T dt plus integration T0 to T1 summation over j equal to 1 to n capital Qj delta Qj dt equal to 0. Here capital T stands for kinetic energy, whereas small t stands for time. Capital Qj is the generalized force, whereas small qj is the generalized coordinate. Or we have integration T0 to T1 summation over j equal to 1 to n del capital T del small qj delta qj plus del capital T del qj dot delta qj dot dt plus integration T0 to T1 summation over j equal to 1 to n capital Qj delta Qj dt equal to 0. Now, integration T0 to T1 del capital T del Qj dot delta Qj dot dt equal to integration T0 to T1 del capital T del Qj dot delta dqj dt dt. If we interchange delta and ddt operation, then we have integration T0 to T1 del capital T del Qj dot delta Qj dot dt equal to integration T0 to T1 del capital T del Qj dot ddt of delta Qj dt equal to del capital T del Qj dot delta Qj at T0 and T1 minus integration T0 to T1 ddt of del capital T del Qj dot delta Qj dt. We have used integrating by parts. We know that for prescribed end configurations, delta Qj at T0 vanishes and delta Qj at T1 also vanishes. So, we have integration T0 to T1 del T del Qj dot delta Qj dot dt equal to minus integration T0 to T1 ddt of del capital T del Qj dot delta Qj dt. Since delta Qj vanishes at T0 and T1, we have already mentioned it. Using the result 5.19, we get integration T0 to T1 summation j equal to 1 to n del t del qj minus ddt del capital T del qj dot delta qj dt plus integration t0 to t1 summation j equal to 1 to n capital Qj delta Qj dt equal to 0. Combining these two, we have integration t0 to t1 summation over j equal to 1 to n del capital T del qj minus ddt of del capital T del qj dot plus capital Qj delta qj dt equal to 0, as delta q1 delta q2 up to delta qn are arbitrary and independent. So, we have del capital T del qj minus ddt of del capital T del qj dot plus capital Qj equal to 0 for j equal to 1, 2 up to n, or ddt of del capital T del qj dot minus del capital T del qj equal to capital Qj for j equal to 1, 2 up to n. These are the Lagrange's equations of motion for non-conservative holonomic dynamical system. These are valid for n degrees of freedom. Lagrange's equations of motion are basically a second order differential equations. Problem. Prove that integration t0 to t1 L function of qj dot t dt and integration t0 to t1 L function of qj dot t plus d capital F dt into dt have the same equations of motion, capital F being an arbitrary function. Let capital I1 equal to integration t0 to t1 L function of qj dot and t plus d capital F dt. Here qj is the generalized coordinate, qj dot is the generalized velocity and t is the time. Thus, I1 equal to integration t0 to t1 L function of qj dot t dt plus integration t0 to t1 ddt of capital F dt equal to integration t0 to t1 L function of generalized coordinate qj, generalized velocity qj dot and time t dt plus capital F at the point t1 minus capital F at the point t0. First term gives the integral I. Therefore, we have capital I1 equal to capital I plus capital F t1 minus capital F t0, where capital I is given by I equal to integration t0 to t1 L function of generalized coordinate qj, generalized velocity qj dot and time t dt. So, delta I1 equal to delta I plus delta operated on the difference of capital F at the point t1 and capital F at the point t0. Since the end configurations are prescribed, so at the end points delta F t1 equal to 0 and delta F t0 equals to 0. So, delta I1 equal to delta I. Therefore, by Hamilton's principle, delta I1 equal to delta I equal to 0, and one gets similar set of equations of motion. Hamilton's principle is very useful in variational principle. It is an integral principle and useful for conservative dynamical system. But there are some non-conservative dynamical systems. So, we have to extend this principle to include non-conservative forces. Using this approach, we have extended Hamilton's principle and used it to obtain Lagrange's equations of motion valid in a non-conservative dynamical system. And with this, we have solved one problem in this module.